You have your screen. Can you switch to
yes.
view? Thank you. So you have 15 minutes.
Thank you. And I would like to thank the organizers for organizing this very nice conference and gathering so many people from different fields, but somehow connected to statistical mechanics on one side and nonlinear dynamics and everything else. So today I'm going to talk about a type of self-organization in complex systems, which is related to the onset of the collective mode and synchronization on one hand, but on the other hand, it will also be related and revolve around the notion of diversity. So this means that the population that I will consider will somehow be comprised of units which do not share their essential dynamical properties, but rather can on their own behave in a very different way. So I will actually present the results obtained in collaboration with my friend from Russia, Vladimir Klinshov. So let me provide a bit of an outline of this talk. So at the beginning, I will provide a bit of a background on diversity and also provide a bit of a reminder on the Kuramoto model, which is actually the essential model of diversity, but not really related to this type of behavior that I will present because it is somehow fundamentally different, though it is about the synchronization and the onset of the synchronization, the onset of the collective mode and the suppression of the collective mode. I will essentially try to first classify the regimes observed in this system, then I will do a bit of the analysis on their local structure and highlight how the interactions that modify actually the local dynamics of the units, and then I will provide a bit of the bifurcation analysis concerning the stability boundaries of the different regimes and the bifurcations in between them. Of course, some part of the talk will be very general and it will concern essentially the system which does not have a fixed distribution of the internal, the intrinsic bifurcation parameters of the system, and then the bifurcation diagram itself will be presented, of course, for the particular form of the distribution of the intrinsic bifurcation parameters. But then I will provide a bit of a short outline on what happens in presence of small noise and small coupling delay. So the fundamental question that I will somehow consider is the presence of heterogeneity in the system. So in many different fields, so from magnetic systems to neuronal populations, many different biological systems, you have like the variability of the units within a single system. So this variability may be called heterogeneity, diversity, it may be called impurities, it may be also seen as the quenched noise or the static disorder. And in principle, it could be both, it could be either dynamical, structural, or both. So we know actually that from the previous work that this type of diversity can actually cause a microscopic ordering of some sort. So it can induce phase transitions, pattern formation, the phenomenon called diversity-induced resonance, where actually the system enhances its ability to respond to sub-threshold signals from the environment, and also it can enhance in a very strange and peculiar way the synchronization abilities of the system. So the case that I will discuss is actually dynamical diversity. So this means that the system is comprised of units which have the intrinsic parameters which are different and that are distributed according to a certain probability distribution. So we have non-uniformity of intrinsic bifurcation parameters of the units, and essentially this dynamical diversity could be quantitative or qualitative. So the typical paradigm of quantitative diversity has been long considered since 1975 by Kuramoto, and we know that in that case we have a population of units which is comprised of intrinsic oscillators, and then somehow they adjust their intrinsic frequencies to give rise to the collective mode. But here I will consider something different. So I will consider the case of qualitative diversity between the units, which means that the population is actually comprised of excitable units, which by themselves are stationary, but somehow they are also non-linear threshold elements, so they can react in a non-linear way to external perturbations. And some of the units could be also oscillatory. So that kind of dynamics is actually typical for neuronal populations, populations of pancreatic beta cells, and other biological systems. So what I want to consider as the fundamental question is actually how are the microscopic regimes of such system and the onset and the suppression of the collective mode affected by such heterogeneity or diversity between the units, which is expressed at the qualitative level. So we know that the basic paradigm actually of many complex systems is synchronization, and we know that from many different books. So there are many different fields from physics, biology, neuroscience, social behavior, chemistry, where actually the units have different intrinsic frequencies, and then they at a certain moment, by just increasing the coupling strength between the units, they provide the collective mode, or they phase lock. So the typical paradigm expressing this idea is actually the Kuramoto model. So as you can see here, this is a model comprised of sinusoidal all-to-all coupled units, a large number of them, and the units have to be weakly coupled because we consider them phase oscillators essentially. And then the distribution of frequencies, as you can see here, is assumed to be unimodal and symmetric. And then, of course, the onset of the macroscopic coherence of the system is characterized by the Kuramoto order parameter. So what can happen is that actually in such a system, we observe the competition between the coupling and diversity. And if the competition is large enough, then the diversity effect is suppressed in such a way that the units tend to synchronize by forming just droplets of first synchronized units which are phase locked, and essentially with the units first which have a relatively common frequency or are close in frequency, and then such a droplet grows. And essentially we have the phase transition of the second order from the state of phase turbulence or the asynchronous state to the state of partial synchronization, and then possibly full synchronization. Now, what is important about that transition is, of course, that it is the kind of second order phase transition. There are some nice reviews about that. And what you can learn from that is that also this type of a model, but including some different ingredients, such as the coupling delay or the phase lag, can also display discontinuous phase transitions. So the phase transitions of the first rather than the second order to partial synchronization. So what I will actually consider is the heterogeneous assembly of delay coupled stochastic active rotators. So why are these active rotators actually interesting? Because they can represent both, they can provide both excitable and the oscillatory dynamics. So contrary to the classical Kuramoto model, where you have just the rotational symmetry of the units, here you have the non-uniform rotation of the units essentially, and the units can also be, depending on this local bifurcation parameter A, there could be either in the excitable or the oscillatory regime, and they actually undergo, just the local dynamics undergoes, as you can see, the sniper bifurcation. So the oscillations occurring for this when this condition is satisfied actually are non-uniform, such that they are slower at the ghost of the fixed point, and they are faster around it. So as you can see here, the other parameters of the system, these are the local frequencies. I will not introduce any kind of like assumption on it at this point. This is the local bifurcation parameter. This is the coupling delay. So this is very typical for many neuronal and other biological systems. And of course, this is additive noise, and the noise terms acting on each unit are assumed to be independent. So this type of noise can actually mimic, for instance, the effect of synaptic noise in neuronal systems. So now what we can do is actually we can go toward the continuum limit, which means that the thermodynamic limit actually of the system. So for increasing the system size to infinity, and then we can actually use the Otton-Thomson formalism. So probably you are very familiar with this formalism. So I will not waste too much time on explaining the basics, but just to let you know that it is just a quick reminder that it is based on the continuity equation, which reflects the preservation of the number of units. And then we introduce the continuum version of the Kuramoto order parameter, as you can see here. And then the essential assumption, which is actually the Otton-Thomson ansatz, is that the long-term dynamics of the probability distribution of the units, which is this F, settles on a particular manifold, which is given by this formula. And the idea is that these complex amplitudes are actually called the local order parameter. Why they're called the local order parameter? Because they express the synchronization, they quantify actually the synchronization of units which are close in frequency. So here we assume that this is a narrow interval centered around a certain frequency omega. So what I want to point out, and which is very important, is the link between the global order parameter, the Kuramoto order parameter, and the local order parameters, which is actually expressed by this self-consistency equation. And this self-consistency equation will later on help us to actually understand the local structure of the stationary states. So what we actually want to find are the macroscopic stationary states of the system, where the global order parameter, the remote order parameter, is stationary. And to this end, we actually do a bit of transformations of the Otton-Thomson equation, and we actually go to polar coordinates. And you can see here that we express it ultimately in this way. And from this equation, we obtain the stationary states. But what is important about this particular derivation is that there appears the quantity called B. So B is actually the macroscopic excitability parameter, or it is called also the resistivity parameter. So it reflects the point that actually the units that are coupled can modify their internal dynamics in such a way that either the excitable units can become oscillatory due to interactions or vice versa. And actually using this macroscopic excitability parameter, which, as you can see, depends on the coupling strength, this non-isochronicity parameter A, and also the global order parameter rho. But so the collective dynamics actually affects the intrinsic dynamics of units and modifies them in a certain way. So the point is that the dynamics of each unit can be expressed again in a form of an active, in a form similar to the inactive rotator, but now this intrinsic verification parameter B is reflecting the collective behavior of the system as well. And from this, one can see that actually under the effect of interactions, the heterogeneous assembly splits into subpopulations of stationary and oscillatory units. So what I wanted to tell you a bit more then is that using this self-consistency equation, one can obtain actually ultimately the expression for the macroscopic excitability parameter, and solving for that, one can obtain actually the different states of the system. And one can also do the local bifurcation analysis of the stationary states, as you can see here, by expressing the Otton-Thomson equation in terms of the real coordinates, as you can see here. And skipping to the more important part is actually what happens for the particular case of a frequency distribution that we have chosen here just for to allow for the complete analytical treatment. And this is the case of a uniform distribution of frequencies on a bounded interval. So we can see here we have a uniform distribution in a certain bounded interval from omega-1 to omega-2, and it is 0 otherwise. So the characteristics of such frequency distribution are its mean frequency and the diversity of the distribution width. So what I want to show you is that actually then one can show that the system actually has three different stationary states. The B1 is actually the homogeneous stationary states where all of the units are excitable. So the macroscopic order parameter is very high, and then none of the units are oscillating. So this state is actually heterogeneous as well, but it's typically unstable in such a system. And this B3 state is actually a heterogeneous stationary state where some of the units are excitable and some of them are oscillatory, but also asynchronous. So the main idea of this
2 minutes.
Thank you. So the main idea of just this analysis is to show the basic organization of the bifurcation diagram. So it has actually three codimension 2 bifurcation points around which is organized. So these are the cusp point over here, the Bogdanov-Takens point, which is the most important one, and the fault homoclinic point. And actually within this region bounded by the two branches of fold curves, actually, and within these regions 3 and 4, one observes bistability. Here, the bistability between two stationary states, and here the bistability of a collective mode born from the Hopf bifurcation and the heterogeneous stationary state. So what I want to show you actually more is that contrary to the classical paradigm where increasing the diversity actually shifts the system from the homogeneous to the heterogeneous stationary state, but just via collective mode, and that this transition is just continuous here due to bistability of the system and the two regions of bistability. We have two additional scenarios which are hysteretic and which you can see here. And what I wanted to show you as well is a bit of the effects of coupling delay and noise. So we consider the effects of small coupling delay and small noise. So basically the qualitative structure of the bifurcation diagram and its organization in terms of the three main codimension 2 bifurcation points is not changed, but the coupling delay actually doesn't change the position of the stationary states and doesn't change the position of the fold bifurcation, but it shifts the hop bifurcation such that actually this region of bistability between two stationary states is increased. And the noise actually does something a bit different. So it changes also the position of the fold bifurcation and the hop bifurcation such that actually it favors the sniper bifurcation scenario, the occurrence of the collective mode via sniper bifurcation rather than the hop bifurcation. So a bit of conclusions, we can see that actually one can determine the local structure of the stationary states from the Otten-Thomson equation, and that we have three different types of collective dynamics. Actually, the homogeneous and the heterogeneous stationary state and the collective